Hello, hello. So, hello everyone. Welcome to the last tutorial of the course Nuclear Astrophysics. So, today we will do some kinematics related problems associated with the nuclear physics, which has been covered in the 8-week course material. So, mainly we will focus on the kinematics part, then we will do some mathematics from that kinematics itself, and then we will go to the some more extra problems which I have taken from a book which I have shown you earlier, and then we will go to the assignments. So mainly today it will be a problem solving session, and as your exams have come, so I think this problem solving session will be useful for you. Okay, so and I will not go into the deep of the detector and I mean some of the important accelerators that I have discussed in the last tutorial, but the theoretical knowledge of the detectors that I will not cover, although I will do some of the problems which are related to those detection of nuclear uh, reactions. So I mean the product of nuclear reactions. So that by doing some of the problems we will touch that topic. So but the important thing of the course 8 material is the kinematics. This part you have to understand really well to do some of the important mathematics. Okay, so what we do in nuclear reactions or nuclear astrophysics course, we have done, oh sorry, let me change, it is fine. Okay, so we generally two nuclei, they reacts and they make some products. So that is our nuclear reactions. So suppose this is the nuclear reaction we talked about. So xy at the parent particle which are taking part in the nuclear reaction, and y and x and small x and capital X at the particle which are taking part in the nuclear reaction, and small y and capital Y at the product nuclei. Okay, so this we can write also like this. Okay. So whenever I write this type of x, that means the capital X, and this x is the small x. So don't get confused in my notation. Similarly, this is capital Y and this is small y. Okay, so in this reaction, this small x we will treat it as a projectile, and that capital X is our target. Okay, and capital Y and small y are the product nuclei. So what happens in a nuclear reaction? Generally, a projectile with some kinetic energy, that with mass m small x, small m with suffix small x, that interacts, I mean it comes towards a higher nucleus. Let us say it is capital M with the subscript of capital X, that means mass of the capital X nuclei. These two generally reacts, and then two product forms. So that means, so it has some kinetic energy, it has some Vx, small Vx, and we consider in lab frame that capital Mx, which is the capital X, that is the target, it do not have any velocity. That means V capital X is 0. So it is at rest, and one projectile with some kinetic energy and velocity is coming towards it, and it will interact with that particle. And then there will be two different products. They also have some of the kinetic energy. So we consider that this is the small y with velocity Vy and mass My, and this is the capital Y. So two products, capital Y, small y, as I told you earlier. So it has a mass of capital M with subscript y and velocity V capital Y. Okay, so this is our consideration, that suppose a projectile is coming, it is interacting with the target, and two products are created and they are going towards some direction, and their direction is like this according to our figure. And we consider that with the uh, path of the projectile, the small y, which makes an angle of theta, and capital Y makes an angle of phi. So this is the understanding of the problems. It is a, you can consider it as a two body collision problem. It is like that, and exactly similar to the, I mean, we can use this formalism of two body collision as the nuclear reaction, in the nuclear reaction mechanism. Okay. So, and here then we have to apply some of the rules of the physics, that means the momentum conservation. Mainly at first we will do that the momentum conservation. So that means, okay, so yeah, so you can see that small y and capital Y, they are these two, they are going at an angle of theta and phi. So we can reduce that velocity in a perpendicular direction in two perpendicular direction, right? That means we can so if the vector, velocity vector looks like this, so we can resolve it into two parts. Okay, so if it is Vy as shown in the figure, then this part will be Vy cos theta and this part will be Vy sin theta. If this you have done in your basic vector analysis course, so that type of thing we can do, and then we will conserve the linear momentum along two direction, that means this x direction and this y direction. So we will write two equation of linear momentum, one is for x direction and one is for y direction. So we are considering in our problem this direction is x and this direction is y. That means the projectile at first it is going towards the x direction, positive x direction. Okay. Okay, so let us write the two equation of conservation of momentum. So my Vy cos phi, that means the x component of velocity of capital M, capital Y mass, okay, plus my Vy cos theta, that is the x component momentum of the small y, that is equals to initial momentum, which was all along x direction. So initial momentum was all along x direction, there was no component of the y direction. Okay, so this is the x direction equation, and similarly if we write the y direction equation, it will be my Vy sin phi plus my Vy sin theta, and as there was no initial momentum along x direction, so that will be 0 y direction. So these are the two momentum conservation equation. So these are the two momentum conservation equation, and this is the basics of the two body collision problem. So always try to remember this figure, I mean how I have defined everything. Okay, so this figure. Okay, now what we will do, we will just do some algebraic manipulation of this equation which I have written here. So what we will do that from the first equation we can write it as my Vy cos phi is equals to mx Vx minus my Vy cos theta. So I have just taken this part, I mean this term on the other side of the equals to sign, and from second we can write my Vy sin phi is equals to my Vy sin theta. So sin theta. Okay, so these two we can write, and now what we will do, we will try to eliminate that phi. This phi we will try to eliminate, and to do that we will do the square of these both equation and we will add it. That means the first term will give you this will give you my square Vy square cos square phi, and this will give you my square Vy square sin square phi. So cos square phi plus sin square phi, that will be 1. That is the main purpose of doing square and adding those to eliminate that phi. So okay, so by doing that my square Vy square is equals to mx square, so mx square Vx square plus my square Vy square minus 2 mx my Vx Vy cos theta. This you can get easily. Square both side and add. Square both equation and add them just. That will give you this. Okay. Now we will use another notation, that is the kinetic energy, and kinetic energy is equals to half mv square. So whenever we get some mv square, then we will try to write it in terms of kinetic energy k. Okay, so that means mv square you can write it as 2k. So from here we will take one my and then my vy square there will be, right, and that my vy square will be 2ky according to this. So this is the process of writing. So that will be, if I write it 2 my ky, I have taken 2 at the front beginning. That is similarly 2 small mx kx. Always remember k is equals to half into mass of that particular element into velocity of that particular velocity square of that particular element. Then 2 my ky minus 4 mx my kx ky cos theta. So just we have converted the mv square into kinetic. I mean rewritten the equation in terms of kinetic energy. And then ky, to get this ky we will divide the whole equation by this 2 my. Okay, so that will give us ky at the left hand side. So that will be mx divided by my kx my divided by m capital Y ky and 2 by my. So this is 4 2 by my mx my kx ky cos theta. This is cos theta. So this is the equation. This is an important equation because here we have expressed our kinetic energy of capital Y element, that means this particular thing, in terms of mass and moment energy of the other particles. That means this is associated to the projectile k small x. This is associated with the small y mass, which is this. Okay, and in terms of their mass and their momentum, and with the angle theta. So here you can see the angle theta is only there, not the phi. Now one thing we can do it from this equation, that we will try to eliminate just let me check it q. Okay, yeah. So one thing we can also do, that we can write the q, which is the q value of a particular equation, that is ky plus k small y minus k small x. You can see there is no term, no k capital X, because we have considered the velocity of capital X is 0. Here velocity of capital X 0, that means this don't have any momentum and this don't have any kinetic energy. So that's why no kx, k capital X will be there. And if we write this in terms of k, then this same equation will be like ky. This you can do by yourself, my divided by my. This is a, I mean, type of expression. If you don't remember this, that is fine, no problem with that. Okay, so this will be mx my kx ky cos theta. And if a special case, if we consider if theta is 90 degree, just a consideration, then your q will be just ky 1 plus my by capital My minus kx 1 minus mx by my. So this is just a specialization. Now you don't have to remember this the special part, but this is important. Okay, just I have just replaced that ky in terms of q. At first, from the momentum conservation equations, these two equations, I have calculated the kinetic energy of capital Y, and then I have replaced that capital Y in terms of q. That is what till now I have done. Okay, now now just a second. Yeah, now consider this equation. This is now our equation which we have got. Now if we multiply this equation with a capital My, so all these are the, I mean, manipulation or algebraic manipulation just to get the required quantity what you want to calculate. Now if you multiply that particular equation with capital My, that is the mass of the capital Y, then MyQ, that will be Ky My plus capital My. So I am just multiplying this equation with a capital My from both sides. Okay, minus Kx My minus Mx minus 2 Mx My Kx Ky cos theta, right? So from here just multiplying by M, just multiplying by My. So don't get confused between x and multiplication sign. Okay, so we got this, and from here we can also write it like this. This is also some term I am taking at first and some I will write at later. So what I am doing actually I am dividing both sides by this particular expression, M mass of small y plus mass of capital Y. Okay, that I am doing. And if you, after doing that, if you do the, I mean, side change, then you will arrive to this equation that I am writing right now. So let me check this. Hello. Yeah, the sound is problem. Okay, so this equation you will get just by dividing this equation by M small y plus capital My. Now this is an important equation because this will tell you many things, like this is the equation of K. Now this equation can be written as Ky minus 2p Ky minus n is equals to 0. That means this Ky, this root over Ky that is here. So that means we have taken p as 2 mx My Kx divided by My plus capital My. This we have considered as our p and a cos theta, right? So that is our p. No, so that is our p. So and n is the last term which I have written in that equation, that is myq plus kx My minus mx divided by My, capital My plus small m. Okay, so this is the equation. So that means this equation can be written like this, where you can think it at a, I mean, equation of order 2 of root over Ky. That means it is like this type of equation: a square minus bx plus c x square minus ax plus b equals to 0. This type of equation, which is the second order equation. And here for this equation you can say x is actually root over Ky. So from here we can calculate the root over Ky as we do in the in our standard mathematics. Okay, so Ky can be written in terms of p and n. That we will do. So that I will again write the important equation: Ky minus 2p Ky minus n is equals to 0. This is the equation we got, and if you calculate it, I mean, if you evaluate the value of root over Ky, which is the variable in our case, that will be p plus minus p square plus n. This is the expression which is very important for the understanding of kinematics of nuclear astrophysics. That means this equation is telling you the root over of kinetic energy of the nuclei, small nuclei, that means that y which was created here. So, in this equation, this was our consideration that x plus small x is giving you capital Y plus small y. Okay. So, you can think small y as the ejected particle. We can as small x we are considering as projectile, so you can say small y is the ejectile. Okay. So, the kinetic energy of the ejected particles, which can be, as you have seen, that can be gamma rays, that can be neutron, proton, or anything, but the capital Y will be higher mass neutron, higher mass nuclei element, but the small y will be just a particle. Sometimes it will be, as I told you, maybe positron, electron, proton, neutron, everything. So, small y is actually called the ejectile. So, kinetic energy of the ejectile, just a second. Yes. So, kinetic energy of the ejectile we have expressed in terms of P and N, where the P and N has been given in terms of the mass, kinetic energy of the other particles which are associated with the experiment. That means we are writing the kinetic energy of this particular material, particular element Y in terms of other element. Okay, that is our sole purpose, and that we have done. Now we will. So, as you have seen that here in this expression we get root ky is equals to some expression p plus minus p square plus n. Now, root ky tells you that ky should be real and positive, because root over negative quantity is imaginary, but the kinetic energy is a real quantity. So, to get the real values we need to have some limitation of ky values, that will be ky is real and positive, then only reaction is possible, because for imaginary value there will be no reaction. So, this is mathematical condition which tells you reaction is possible or not. Now, we will consider some part, I mean we will consider some of the cases like let me go to the blue. So, case 1. So, for case 1 we will consider q equals greater than 0, that means the q value is greater than 0, and under this case Roman 1 we will consider two more cases. That is, for first, that projectile has very less energy, very low energy. That means that kx, which is the energy of the projectile, that is almost equals to 0. That is our consideration, assumption. We will see what it will give. Okay. Then that means your kx equals to 0 means in P, here is the kx lying here, right, root over kx. So, this, if kx equals to 0, that means your P is equals to 0, right, that will give you P is equals to 0, and this term here, this kx will be also 0. So, the second term in the numerator, that is 0, only n will be myq, the first term in the numerator, by the denominator as it is. Okay. Then your ky, root over ky, sorry, which was p plus minus p square plus n, and for our case p is equals to 0 and we have only n, that means your ky is equals to n, and that is equals to myq by my plus small my. So, this is the kinetic energy of the ejectile if the projectile energy is very less and q value is greater than 0. So, under these two conditions, that just remember the two conditions, the q is greater than 0 and projectile has very less energy, then you can write the energy of your ejectile ky as mass of the other project, that is capital Y times of q divided by the mass of the ejectile plus that other project. So that you can write, and you can see that as our p is 0 for this particular case, that means this cos theta dependency is not there in the problem, because p is itself 0. So we can say that it is same for all values of angle theta, because there is no theta dependency here due to the p 0 value of p. So this was the first consideration under case 1, and the second consideration is finite projectile energy. So first we have considered the projectile has a very less energy. Now finite energy projectile. Finite energy projectile. That means kx is not nearly 0, is greater than 0. Okay. And under this consideration, you have also another, you have to assume another thing, that I mean this is the realistic scenario, that under this consideration it has been shown that it is shown that in most cases that mx is very less than my. Why I am telling it, like, just a second, I will tell you with an example. Okay, so like this is the example, Newton plus 14n, that will give you 11b plus alpha particle. Okay, yeah. So that means that for this equation, if we want to write is in terms of as we have written x plus x equals to capital Y plus small y. So you can see for this equation, x is actually the Newton, small x, and the capital X is 14 nitrogen, and you know that mass of Newton is very less than mass of the 14 nitrogen, right? Because there is only 1 Newton, and in 14 nitrogen there are 7 Newton. So this consideration is valid. That means your mx, m of small x, is very less than capital M of small oh sorry, one second, that let me check. Oh, capital Y we are talking about. Okay, so M11p. So it is also true, because 11b is much higher than the single Newton. Okay, that means this consideration is valid under this assumption. So this is our assumption that mx, m of small x, is very less than capital My, that is mass of the projectile is very less of the mass of the project. I mean the project nuclei, not the ejectile. Okay, so and under this condition, your n, which has been written here, p and n, just try to remember that p and n. It is very useful if you can remember that p expression, n expression, and the equation that root over ky equals to p plus minus p square plus n. It will be very beneficial or useful to you. So under this condition, you can see n is greater than 0 for all kx. I mean whatever the value of kx with a finite value, n will be greater than 0. That means our equation, which was ky is p plus minus p square plus n, this equation is single valued. So ky is single valued for all k small x, and it can be given by, and is given by ky is p, just a second, whether it is plus or minus, I have to check it. Just give me some moment. Yes, yeah, and it will be given by root ky is equals to p plus p square plus n. So we have omitted the minus sign. This is the realistic scenario, that if there is finite energy projectile, and the consideration of m small x is very less than m small y, then n is equals to 0. That can be shown for all kx, and ky I mean k small y is single valued, which can be expressed by this. So you may face some of the problems which can be solved by this particular equation. Now there is another part of this assumption that I will come later, but the other second case is much important. So here there was another part, that's why I am giving a start, that I will come later. Okay. Now till now I have considered the q greater than 0 and under q greater than 0 two other assumptions are there. Now case 2 where your q is less than 0, that is also possible, and again we will assume that projectile has very low energy. So we have done q greater than 0, low energy projectile, finite energy projectile. Now we will do q less than 0, low energy projectile, finite energy projectile. That is the total 4 case we are studying. This is under case 1, this is under case 2 that we are doing here. So projectile has very low energy, that means again kx is nearly 0. That means again your p is 0 and n is myq as previous, my plus capital My. Okay. Sorry. Yes, q less than 0. Oh no. Just, for low energy projectile kx equals to 0, yes, and q less than 0. That means q less than 0. Okay, let us now go to that p. So let me put this 2 here. Yes, yeah. Okay. So here just consider that we have taken q less than 0, right? That means square plus n, and our equation which was root over ky is p plus minus p square plus n. Okay. So kx equals to 0 means this is 0, that is p equals to 0. So ky will be n, root over ky will be root over n, that we can write, and p square plus okay. So it is yeah. Now if your kx equals to 0, understand it quite well. So that means this term is 0, right? This term is 0. That means your n is myq by my plus my, and in this case 2 we have considered q is less than also 0. That means this particular element is also less than 0. That means your n is less than 0. Why? Because capital My or small my, all those are all positive values, mass, that cannot be negative, but the q itself is negative and it is sitting in the numerator of the expression n. That will make the sign of the n is negative. That means n less than 0. And if your n less than 0 and if you put your n here, that means you are taking root of a negative quantity, which will give you an imaginary value of ky, which is not possible in the realistic scenario. Ky cannot be imaginary. Okay, so under this condition, q less than 0 condition with very small energy of the projectile, we are getting a imaginary value of ky. So I am writing imaginary value of ky, which is not possible. That means under this condition there will be no nuclear reaction. Okay, so understand it very well. If your q value is less than 0 for a equation and your kinetic energy of the projectile is closely 0, then the reaction is not possible. Is not possible, right? It is not possible. That tells that you must have, so we must have a finite value finite non-zero value of kx so that the reaction occurs. Reaction takes place. So we must have a finite non-zero value of kx, that means the projectile energy, so that the reaction takes place. From here, the situation of threshold energy comes into the picture, that you have seen that with zero energy value the reaction is not possible if it is a endoergic reaction, that means q less than 0. The reaction is only possible if kx has a finite amount of energy, which is called the threshold energy. So now you can understand how the threshold energy comes into the picture of the nuclear reaction if it is a endoergic reaction, if it is q less than 0. But if your q is greater than 0, that condition doesn't happen, because here that n will be positive for q value of positive, so there will be no imaginary part. Only when your q is negative, then the imaginary situation arises. Okay, so this was the thing. So that is, from here I will write here, the threshold energy understanding comes into the picture. Threshold energy, which is the minimum energy of projectile required for the reaction to happen. Okay, only under the only for those reactions which has q less than 0. Okay, so this threshold energy can be calculated by a criteria, that is p square plus n equals to 0. If you calculate, so this is the criteria of threshold energy. This is the criteria, and you know what is the p and n, already we have done it. So just put that value p square and n, then you will get the condition which should be the threshold energy of the projectile. Okay, and on so p square, that was here, from here we will put that. So p square is actually mx my kx divided by my plus my square cos square theta, right? There is a cos theta, yes, and that n is myq plus kx my minus mx divided by my plus my, that is 0. So this is the condition of the threshold energy, and the minimum possible value of kx is at theta equals to 0. So we will consider theta is equals to 0. That will that means the cos square theta term will not be there, because cos square 0 is 1. Okay, okay, and because we are considering that the projectile is coming to us along the x-axis, so there is no theta in our thing, I mean in our projectile, so there is no angle for the projectile. Okay, so and this will give you the minimum estimate. So if we do it, and so I will not do the all the steps now, we will just solve this equation, and some substitution we will do, that we will write my is mx plus, so it is coming from the conservation of mass only. Okay, so that means conservation of mass says m small x small x plus capital Mx, that is small my plus capital My. That means we can write small my in terms of mx plus capital Mx minus capital My. This we can write, and we will just after the calculation of this particular equation, we will just substitute that my whenever the my comes in terms of this. If you do that, I will not do, I mean just do it, simplify it, just simplify it. it will take much time. I mean, this is very easy, but time taking. Okay, so you will get that E threshold will be minus q mx plus mx by capital Mx. So don't get confused, because in the class, I mean in the class material, that E threshold expression was different, but the value will be same. I mean, those are same. I have just substituted this exact thing. If you substitute this capital Mx plus small mx in terms of capital My plus small my, you will get that expression also. I mean, that type of change you can always do. So this both of these expressions are exactly similar, because I think in there it has been written like this. So mx plus mx, it has been written as my plus capital My, and again m capital X, you can write it like this, right, from here. So that is same, exactly same. I will consider this particular thing because it is easier to express, because only 1, 2 and I mean in the numerator there is only 2 term, and in denominator there is only 1 term. So I will use this particular expression, but both this expression are exactly similar, same. So ETH can be written as minus q 1 plus mx by m. I have just divided the numerator by the denominator. Now consider this minus sign. This minus sign is very important, because this minus will automatically come if you simplify that expression which I have written, because in this condition the main important thing is q less than 0. That means suppose q is minus 2. So whenever you put q minus 2 here, and there is again a minus sign in front of that minus 2, which will make is plus 2, and I mean mass of elements are always positive, so that will give you a positive value of energy, right, because energy cannot be negative. So that this minus sign is an important one. Always remember that. So I will write this expression, because this type of problem you can find mx by my, E threshold. So E threshold is 1 plus mass of the projectile by mass of the product, 1 plus that quantity, and it will be multiplied by that q. Okay. So from here we will do a simple problem on the threshold value. Sorry, what happened? Yeah. Okay, so we will consider a particular reaction, and then we will calculate the threshold value associated with that reaction. So that example which I taken earlier, Newton. So this is the 14 n alpha 11b. That is the reaction, x plus x, y plus y type of reaction. Here for this particular case, x is n, small x is n, capital X is 14 n, capital Y is 11b, and small y is alpha. Okay. So I will calculate the threshold energy which is required for the Newton, so that the equation occurs. And masses are given. So mass of reactant, that means small x plus capital X, what I am writing, reactants. Okay, that is for 14n it has been given as 14007550. For Newton it is given 1.008987. This will be given in your problem. Okay, so that is 15.016537 in AMU unit. And mass of products, that is for alpha it is 4.003879, and for 11b it is 11.012811. Okay, that is 15.016690. Now if we calculate the q value, it will be, so 15.016537 minus 15.016690 u, that will give you minus of 0.000153. and if we multiply it with the energy, so multiplied by 931 mega electron volt, that will give you minus 0.14 mega electron volt. So you can see that Q is negative. Q is negative. That means Q value is telling it is endoergic reaction. And I have told you that for endoergic reaction there should be some threshold value. If by calculation it can also be asked like this, that you have given an equation and you have to calculate the threshold value of the projectile, but while doing the calculation you are getting a positive value of Q. In that equation there will be no threshold energy, just it is the question is trying to test your understanding whether you have understood it well or not. So whenever you, although it has been asked for the threshold value, but the answer will be that for that particular reaction, if you get Q is greater than 0, there will be no threshold value of the projectile. If you get Q less than 0 or negative, only then the threshold value, I mean the threshold energy will come into the picture. Please remember that. Okay, so if we calculate the threshold value, E threshold is minus Q 1 plus m small x by m capital. Oh, just a second. Yeah, sorry. So here it will be, very sorry for that, it will be capital X, not capital Y. Okay. Because yeah, mx, capital Mx by mx will give you 1 and small mx by capital Mx term will be there. Yeah. Okay. So sorry for that. It will be small capital Mx in the denominator. Just I mean correct it. Okay. So this was the thing. So minus 0.14. You can see this minus and this minus will be cancelled out. 1 plus mass of small x. So our small x was Newton, and for Newton the mass is given as 1.008987 divided by mass of capital X. Capital X is nitrogen 14N, which is this. So it is given as 14.007550. Okay. Now if you do that, you will get the value as 0.15 mV. Okay. So this is the threshold value of the projectile for our case, which is Newton. So if the Newton has energy, greater than or equal to 0.15 MeV, which is the threshold, then only the reaction will occur. If it has less than 0.15 MeV energy, the reaction will not happen. For this case, the reaction will happen. Okay. So this is the importance of understanding the threshold energy calculation, and which is important for endoergic nuclear reaction if your Q is less than 0. Just a second. Yeah. Now the kinematics part, most of the kinematics part is done, but I mean the theoretical understanding is already done. Now we will go to some of the examples associated with this problem. Okay. So just a second. Yeah, it's 641. Later. Yeah. Yeah. So we will do some applications of this kinematics which we have studied. Now there is a question. So example problem. Okay. So suppose reaction that is given 7 Li P N 7 B. That means proton is reacting with 7 Li, which is giving 7 beryllium plus 9 neutron. So this is our reaction. Now this is given, the mass of 7 Li, P, N and 7 B all are given in the problem, and you have to calculate, and one thing also given. So as I told you, so this was the projectile, this was the target. After reaction they will go like this. This was the small y, this was the capital Y, this was theta, this was phi, according to our picture, right? Can you remember? Here, this picture. Okay, so this, I mean, for this reaction also the picture will look like this, and it is given that this reaction is happening with an angle theta equals to 30 degree. This is given in the question. Okay, and masses are all given, so you have to calculate. So the question asks the calculate the energy, bombarding energy means energy of the projectile, that is the bombarding energy. Okay, so this type of language also used. So bombarding energy which for which newtons of zero energy, so the ejectile has zero energy, would be obtained. This is the question, that you have given a reaction, you have given masses of the all reactants and products, the angle theta is also given. Now we have been asked to calculate the bombarding energy, that is the kinetic energy of the neutron, kinetic energy of the proton, which is the projectile, for which newtons of zero energy would be obtained. That is our question. Okay, so let us now calculate the q value at first. So q value will be, I mean, just a second, masses are given. So 7 Li, that mass has 7.0160 in U unit. P, proton, has a mass of 1.0078. Then 7 beryllium has a mass of 7.0169, and neutron has a mass of 1.0087. All are in U unit. These are given in the question. So if we calculate the q value, it will be, I will not say because it is has already done many times, so just follow the what I am doing. So it is minus 0.0018 u, and again if you multiply it with the 931 MeV, then your answer will be, I mean, just multiply it, that minus 1.67 MeV. Okay, so we are getting q negative, that means it is also endoergic equation. So sometimes this type of question can also be asked, that what type of reaction is this, whether endoergic or exoergic. You have just to have to calculate the q value, that will tell you. Okay, so according to the problem statement, we want to calculate that kx for which ky equals to 0, that means zero energy of neutron, for which kx, the neutron energy is 0, that we have to calculate. Okay, so the famous equation, that ky is equals to p plus minus p square plus n. We are again going back to that equation. That is the most important equation in this kinematics, I will say you again. And we need ky equals to 0 according to this problem, that means 0 p square plus n. Now you take p to this side, square both sides, that means p square is equals to p square plus n, that means p square will be cancelled out and n will be 0, right, under this consideration. And n, expression of n you also know this one. So n equals to 0 means this right hand side is equals to 0. Oh, sorry, just a second. Yeah, sorry for that. So n equals to 0, that means the right hand side expression of n, we will equate it to 0. So my cube plus kx my minus mx divided by my plus my, that is 0. So this is the condition we need to solve our problem, that for which energy of projectile we get 0 kinetic energy of neutrons. Okay, so if you calculate it to be 0, you will get that kx is minus my cube by my minus mx. just do it. Few one or two lines will be there. Now all these values of my, mx are given, and q value is also given, so we can calculate the energy of projectile for this problem. So my is given as 7.0169 and q was 167. So q has a minus sign, this minus sign will cancel this minus sign, that this the whole thing will be positive, and my minus mx, that means 7.0169 minus 1.0078. so this will be your answer. Okay, yeah, 7 which you can calculate, and it will be, the answer will be 1.95 MeV. So we got kx is 1.95 MeV. That means according to this problem, that if our projectile proton has a energy of 1.95 MeV, then the ejectile, which we got as neutrons, that has zero energy. Okay. So this type of problem, this type of small problems may be there. Just the main thing was this equation, ky is equals to p plus minus p square plus root over n, and according to your problem it was given that ky is 0. We have just put the value of ky is 0, and that gives us the condition that n should also be 0, and we know the expression of n. By putting that expression and equating it to 0, we get the value of kx. Okay. So this is one type of problem which can be asked from the kinematics of nuclear reactions. Okay, very good. Now we will do some other problems. Yeah, just a second. 6.4, 6.3. Yeah. Okay. So let me see. Okay. Now we will do another problem. So another example. Yeah. So this problem tells that 23592 uranium, it captures a thermal neutron. It captures thermal neutron, that means neutron induced reaction, and fissions to release energy of 180 MeV. Okay. Now it is telling that if the mass number of fragments that has been created due to the fission, fragments P 140 and 93, calculate the kinetic energy, I am writing it as Ke, of the lighter fragment. This is a question, that 92 uranium 235, it captures a thermal neutron, that means neutron plus 92 U 235, and then fissions, and it makes two product, which product it has not been said, with 140 plus B 93, I am writing as 140, A and B, and it releases energy of 180 MeV. That means Q is equals to 180 MeV. It has been given. Energy released means plus positive Q, exergic reaction. That means positive of 180 MeV is the value of the Q. Okay, so this is the reaction. It has been given in our problem, and it has been asked to calculate the kinetic energy of the lighter fragment. That means we have to calculate the kinetic energy of 93B. Okay, so again if we just compare it with our thing, so this is lighter element we have written as small y, and heavier capital Y. So this is the reaction, and we have to calculate the kinetic energy of the lighter element, that means ky. Ky we have to calculate what is the value of the ky. Okay, so I am just trying to put the given problem in terms of the theoretical understanding we have done. That's why I am writing it as small x, capital X, small y, capital Y, so that it will be easier to compare it with the theoretical knowledge. Okay, now so one thing is very important, one term, that is it is said thermal Newton. Okay, and you have seen previously in your course that thermal Newton means those neutrons which has very less energy. So we will assume, according by reading the problem statements, that thermal that thermal Newton means the energy of neutrons, that is E small x, this thing is very close to 0, almost 0. That is our consideration. Okay, so Ex equals to 0. That means let us again go to our P. So where is our P? Yeah, P is here. Oh, Ex, not E. So I mean E is also fine, but as we have followed the notation of K, write it as K. That is the kinetic energy. E is also a way to represent the energy, but we will stick to the K notation, which is K is our kinetic energy. Okay. So Kx equals to 0, it is given. That means if we go to our P, where was that? This P, this Kx equals to 0, it is given. That means P is again 0. Okay, so Kx equals to 0 gives us P is equals to 0. That means that means Ky P plus minus P square plus n. Okay, P is 0, that means your Ky is only n, because this P will not be there because they are 0, and we know the expression of n. Again put it here, my minus, I am just copying from my notes, my plus m of y. Okay, so this is the thing, and again put Kx equals to 0 here in this expression, so no need to write that second term in the numerator. It will be like this only, capital My cube by small y plus small my plus capital My. Okay, so this is the expression of Ky, and under the consideration that Kx equals to 0 as given in the problem. So you have to identify that what the thermal Newton means your energy of the neutron is very low, that is close to 0. So if you put your My cube, so My is given, right? M capital Y is 140 divided by 140 plus 93, and Q value is given 180 MeV. So this will be the answer, which will come as 108 MeV. That means the kinetic energy of the lighter element, that is Ky, is 108 MeV. Okay. So this type of small problems may come, and all the solutions are lying in the expression of P and expression of N, and that equation Ky is equals to P plus minus P square plus N. So these three expressions are main important expression. If you can remember it, it will be very useful to you. I am again saying this, and all this type of questions you can solve it by just calculating the value of P and N. That will give you everything you want for your problem according to your problem. Just put the conditions which has been given different for different problems. Okay, like this problem, the conditions was Kx equals to 0. For the previous thing, it was the condition was ky is equals to 0. So what type of conditions is given in the exam, according to that, I mean given in the problem, according to that you will get the solution which has been asked for. So these two example we have already done. Then we will do another thing. So this we will do as a problem, I mean theoretical problem, I can say it. So I will do it what I want. Okay, so my page is finished. Let me go to the here there is some pages. If required I will erase some of those, no problem. From here I will start. Okay, so this problem tells that another example. So two problems I have done. This is the third problem. Yes, so this problem tells you that assuming the collision to be elastic, that we have already considered. So by using the Q equation, that the kinetic energy kx, k of capital X, okay, kinetic energy of the target particle just a second, ky, kx, yeah, something missing here, kx, elastic correction I am putting, just give me a second. Okay. Okay, this problem I will come later because it needs some more understanding, that I will come at a later time. But other two problems is fine, no problem. Here you have to consider some more assumptions, then only you can calculate, because it has been asked to calculate the kinetic energy of k capital X under the consideration of elastic collision. But in the theoretical background, we have considered the kinetic energy of capital X is 0. So this is another type of problem that I will do later. Okay, but the other two problems are fine and they are easy to solve. This example 2 and this example 1. So this was example 1 and this was example 2. Okay. I will come to that. Okay, so now we will go to some of the problems. Let me see. Yeah, here these are more extra problems which are related to detectors, accelerators, also the kinematics of the reactions. So it will be a brush up for you for the material of 7th week also. Now what this 3.2.1 problem asks said that the total photon. So now we are changing gear a little bit from the kinematics to the matter radiation interaction, which has been covered in the materials also, detectors, all those things. Okay, so just a change of topic. Now in this question it has been asked that but these topics are already been covered. So the total photon absorption coefficient for 5 MeV photons in lead is about 0.04 centimeter square per gram, and the density of the lead is given 11.3 gram per centimeter cube. Now we have to calculate what is the thickness to have the intensity of 5 MeV photon beam. What is the PV thickness to have the intensity of 5 MeV photon beam? What is the thickness to allow a 5% beam survival? Okay, half. Oh, that I was that I have missed. So what is the lead thickness to half the intensity of 5 MeV? That we have to calculate, and also 5% of the beam survival. For that we have to also calculate the thickness. Now as I have told you, and you have already seen, that whenever photons or gamma rays, because gamma rays are actually high energy photons, they go through the matter, it will be reduced, the intensity will be reduced, because some of the gamma rays or photons will be absorbed inside the matter. And if suppose this is the thickness of a matter and gamma rays or photons are going like this, and suppose n0 number of photons are falling on that material, and there will be some absorption inside of the material, that is the interaction of light and matter. Due to that, and the intensity which will come as the outside, it will be different. So if it is n1, this n1 will not be equals to n0, this n1 will be different from n0, and that can be expressed at, so if the thickness is t, then n1 is actually n0 e to the power minus mu t. So you can express the photon energy which is coming out of that material by this equation, which relates it the outcoming radiation with the incidence radiation. That is the theoretical understanding we need to understand. So I am writing it, the number of photons as a function of the matter thickness x, if the matter thickness is x, is can be written as, so n with the thickness of x is n0 e to the power minus mu x. Okay. So that means nx is the intensity after the radiation passed through a material with thickness x. Okay. And according to our question, we have to calculate the thickness for which the intensity will be half of the incident intensity. That means our nx is n0 by 2, where n0 was the incidence thickness. This is given. So it is a very, simple problem, but an important one. So we will denote it as x half. That means at a distance of x half, the intensity will be halved. So half is the subscript of x. So we can calculate the x half as ln2 by mu. Just take the log from both sides and you will reach to this particular expression. So this was half is equals to e to the power mu x half, and then take natural log both sides, and this will be your answer, 17.33 gram per centimeter square. So this will be your answer in terms of gram per centimeter square. So this is the thickness, and it is given that the density, so rho of PV lead, the density rho is 11.3 gram per centimeter cube. So from here you can calculate what will be the thickness in terms of centimeter. So your thickness will be, that is L half is actually x half by rho. So you can see your x half as a dimension of gram per centimeter square or unit of gram per centimeter square, and it has a gram per centimeter cube. Gram will be cancelled out, and 1 centimeter will be in the gram by centimeter. Yes. So this will come above, and the dimension will be centimeter, right? Because it is by gram by centimeter square. So that is x half we have already calculated 17.33, and rho is given by 11.3. What value we will get will be in linear scale, that is in centimeter, and the value will be 1.53 centimeter. Okay, so this is the value of thickness for which the radiation will be halved of the incidence radiation, which is exactly coming from this thing. Just consider one thing, that here x, which we have been used as a proxy of the thickness, that is actually comes as unit of gram per centimeter square. Okay, it is how it is defined. So from that gram per centimeter square, by dividing with the density, we have to go to the linear scale of the thickness, which is the L half. This you have to remember. This x is not itself the answer. Now again, for a 5% survival, so the second part of the question, that what is the thickness to allow a 5% beam survival. So for a 5% beam survival, that means 90% have already been absorbed. Okay, so again nx is n0 e to the power minus mu x, and your x here it is has been told that nx is 5%, that means 0.05 of n0, that is 5%, and we will write that like this. So again just take the log from both sides and you will get your answer. X will be minus 1 by mu log of 0.05, which will give you 75 gram per centimeter square, and the length or the thickness, that will be this 75 gram per centimeter square divided by the density as before, gram per centimeter cube, which will give you 6.63 centimeter. So you can see that for a thickness of 1.53 centimeter, the radiation will be halved, and for a thickness of 6.63 centimeter of the same material, the radiation will be 5%. Okay, so from here you can also understand that the radiation is falling like a exponential, that means it is following a exponential decay law. Okay, so this was the problem. It has been taken from that book which I showed you in the previous lecture. That book is very good book for practice of I mean the collection of the problems is very good in that book, and the solutions are also given. So this is a book of problem and solution of nuclear physics, which can be used in our astrophysics purpose also. Okay. Yeah. Now we will go to a problem of time of flight method, which has been covered in the last class. That time of in the detector part, the time of flight method is a is a way to detect various nuclear reactions or various products. So we will not go into the detector itself, but we will do some problems on the topic. Okay. So you know that in the time of flight problem, there will be a starting point, there will be an ending point. If the distance is L, then L by V will be the time of the flight, that means the time the particle need to reach from the starting to the end. This type of mechanism generally governs the time of flight experiment. Okay, so let us do what type of problem is given. Let us go through it. That two equal scintillation counter S1 and S2 1 centimeter thick placed on a beam line at a relative distance of 3 meter. As I told you that the distance it will be 3 meter are used to measure. I have taken some part of this problem because there were, you can see there is two questions 1 and 2, but there was actually 4 questions. I don't find the third and fourth one relevant to this course, that's why I have not taken that. So it may appear to you that there are some much more information for the problems, but those informations are to solve those 3 and 4th part. Just consider that part which is required for our course. Okay, so as I told you that it is separated at a distance of 3 meter, and then all the particles in the beam line have the same momentum p. Okay, so this has been given, which is relevant for our problem to solve one. Now we have to show that in the limit E greater than m, so don't confuse it, it is actually mc square. For this problem they have taken the c is equals to 1, that is the separate thing that you can always do, E greater than mc square actually. Okay, and and the following relation holds for the difference between the time of flight of two particles having square mass difference of this. So delta m square is m1 square minus m2 square. We have to express the time of difference of the flight time of two particles, because here you have, it is given that two particles are there, that is m1 and with mass m1 and m2. We have to find the difference of their time of flight. That is the main thing of the problem we have to do. Okay. So here it is given delta t is t2, which is required for the particle 2, minus t1, which is the time required for particle 1, time of flight. That we will do. But this is a relativistic problem, because particles are moving with relativistic velocity, so we will use some of the relativistic approach. I mean, and as it is a course for graduate student or undergraduate or postgraduate student, I think you have some idea of the general theory of at least special theory of relativity that is required for this course. So in our special theory of relativity, we use a factor of Lorentz, called Lorentz factor, that is gamma. So gamma can be written as 1 minus v square by c square. So this you know that if our velocity of a particle is very nearly to c, then we come to the relativistic regime, and in that case the relativistic limits are important. So gamma is 1 minus v square by c square, and v by c we also express it as beta. So beta factor it is called, just a factor. So that means it is 1 minus beta square. Okay, and from here you can write also 1 by beta is 1 minus 1 by gamma square. This you can write. Sorry. Okay, this much we need only from the relativistic thing. So this is the Lorentz factor gamma, and beta can be written like this. Now one condition it is given that your E is very less than mc square. That means its energy is very high, and energy is very high, that implies the gamma is very greater than 1. Okay, this is the relativistic thing. And if your gamma is very greater than 1, that means 1 by gamma is very less than 1. This is also right. Okay, so and if you have, suppose you have something like this 1 minus x square, and your x is very less than 1, that means you can suppose x is going to 0. If this expression is given, you can approximate this expression as 1 plus half x square. This approximation you can always do under the consideration of x is very less than 1, that means x tends to 0. Similarly, we have got expression 1 minus 1 by gamma square for this problem, where our this 1 by gamma term is very less than 0, less than 1, that means 1 by gamma is going to a 0. That means we can also approximate it like this. This is the same thing, the approximation which I shown you according to this. So 1 by beta, so 1 by beta under the consideration of E is very greater than mc square, we can write is 1 plus half by gamma square. This we can write. Okay, now the second part is very easy. So we have already established that 1 by beta is 1 plus half into 1 by gamma square. Now difference between them, the flight of time is t1 minus t2. That means the length which has given us 3 meter, so that L divided by the velocity of first particle, say v1, and velocity of the second particle, this will give you the time. And as I have written, v by c equals to beta, that means v1 by c can be written as beta 1, and v2 by c can be written as beta 2. This is nothing, just I want to express the velocity in terms of beta. So that means L v1 will be beta 1c minus L it will be beta 2c, like this. If you go through, I mean, after doing this particular problem, if the values of velocity is given, you can also numerically you can do the numerical calculation and find an answer also. Okay, so just follow this method what I am doing. So you take L by C common, 1 by beta 1 minus 1 by beta 2, and you just put your 1 by beta which has been written here. That means 1 plus half 1 by gamma 1 square, because for particle 1 we are using this, 1 minus half 1 by gamma 2 square. 1 and 1 will be cancelled out, So it will be L by 2C 1 by gamma 1 square minus 1 by gamma 2 square, right? It will be like this. And in theoretical and in relativistic regime, we have some other relation, that is E, that is the total energy of a particle which have a velocity v, that means which is very nearly to c. That for that we can write the total energy as gamma mc square and the momentum as gamma mc, because in the relativistic limit E equals to pc, this holds for relativistic. Okay, for relativistic limit it holds. So you can write that just a second, yes, that it is correct. So what we can write, okay, so we will use this particular thing, that 1 by gamma is mc square by E, and we will put that here L by 2c. So 1 by gamma is m1 c gamma square we have to put, that is m1 square c to the power 4 by E1 square minus m2 square c to the power 4 by E2 square. Okay, and also I have written E is equals to pc, right? So if we write that m1 square c to the power 4 is there, E square means p square c p1 square c square, because for first particle, and similarly E2 is p2 square c square. Okay, so I mean c to the power 4 by c square will give you a c square term only. So that means L by 2c m1 c square by p1 square m2 c square by p2 square, where p1 p2 are momentum of that particle, and the problem it has been given that they have same momentum p. That means p1 is equals to p2 is equals to p. It is given in the problem. So if we just put that L by 2c m1 c square by p square minus m2 c square by p square, that means L by 2c, we can take that p square common, that will be m1 minus m2 c square by p square. Okay, yes, and it will be L by 2c delta m c square by p square. Okay, so this is the result we got from this delta t. Delta t is equals to L by 2c delta m c square by p square, and but you can see that their expression don't have c square here. I have got an extra c square because I have considered E greater than E is very greater than m c square, not m. If you consider E is very greater than m only, and if you take the c as 1, which is the natural unit, then in the expression the c will not be there. You can do it in that way also, no problem. Then you will not get that c. Okay, because in natural unit we have taken that c is equals to 1. So what I have got is exactly similar with this expression. It is your choice whether you want to do it with c or no c. I mean c is 1. So these two are exactly similar. Don't confuse between that, because in high energy physics we generally write E very greater than mc square as E very greater than m, and we express m in terms of c square. That is a different thing, but follow the procedure what I have used in this problem. Okay. But you will get the same result. It is a matter of taking c as one value or c itself. This is a light speed of light. So this was the problem, and this was the first part, and the second part asked you to calculate, this delta t for which the value of p is given and the mass of is given, because this mass is needed because of delta m, which will be m1 minus m2, so that you will get from this, and your p is also given, and L is also given as 3 meter, and the value of c is 3 into 10 to the power 8 meter per second, which is tangent value. So just put those values and you will get a numerical value of delta t. So that is the second problem. Just in the first part they have asked us to calculate the delta t in terms of the some parameters, I mean AL, C, delta M, P, and in the second part you have been asked to just calculate the numerical value. So if I do it in their way, it will be P square, which we have done. L is given as 3 meter, sorry, this is C. It is 2 into 3 into 10 to the power 8 meter per second. Okay, and you can see the delta M1 and M2 value was given 493 MeV by C square, 139 MeV by C square. That means 0, that is MeV. So if I convert that MeV, 493 MeV will be 0.493 GeV minus 0.139 GeV. Why I have converted into GeV? Because my P is given in GeV, so I will use 1 instead of 10 cube MeV. So all those values I have converted into GeV. So if you put it, your answer will be 1.12 nanoseconds. That is the answer. That is the difference between their time of flight. So the unit of time is coming from this particular thing only, that meter per second. It will go above and it will give you the time of unit of time for the problem. So this was a problem related to the time of flight. That is a good problem. Now let us go to the assignment, the final assignment, assignment 8. Okay, so this was the some problems, extra problems, which I have been gathered from some of the books. Okay, now let us go to assignment 8, and if I have some time at the end, I will do some more things. Just a second. Okay, so yes, so up to this point there is no need of giving that. This line is just given to give you some idea about the astrophysics, so that is not needed. Our main focus will be this part, that to study the interaction of protons with 12C, an experiment is being performed. A mylar, which is a compound C10H8O4, which is a target foil of so we have a mylar target foil with some thickness, and is bombarded with 10 MeV protons. So these are protons of 10 MeV. These are bombarded with the mylar target. Calculate the number of 12C nuclei present per centimeter square of the target foil. Okay, that means you can see that target foil is a combination of C10H8O4. That means we have to calculate the number of 12C, that is C this part, present in per centimeter square of the target foil. Okay, so no need of giving this 10 MeV, newtons, all this. We have to just calculate the number of carbons in a particular compound. That is the main problem here. So you can see, if you calculate that just a second, mass percentage of yeah, if you just calculate the mass fraction, that means you have C1C has a 12 mass, that means 10C has 120 mass, hydrogen has 8, and also oxygen, one oxygen has 16 mass. So if you calculate, I will not do that, that mass of carbon in mylar you will get is 62.5%. Okay, I mean this will become as 10 times 12 plus 8 times 1 plus 16 times 4. This will be the total mass, out of which 120 is the mass of the carbon itself. All this I am talking in AMU unit. So from that you will get the 62.5% is in carbon nuclei, carbon element, or whatever you can say. Now what we have also given that, yes, so that means if you have 100 gram of mylar, there will be 62.5 gram of carbon, because that's why we have written it in percentage, so that we can convert it in anything. That means, and the thickness is 2.0 mg centimeter square thickness. So it has carbon, exactly 62.5% of 2, that will give you 1.25 mg per centimeter square. Okay, and you have to calculate the number of 12 nuclei in that particular material. So it will be come as, I mean, 6 point Avogadro number is 6.022 or 23 to 10 to the power 23 will be in a single mole. We have 1.25 into 10 to the power minus 3 gram per centimeter square. Milligram has been converted into gram, and 1 carbon has 12 gram. Okay, so this will tell you number of nuclei in per area, that will be 6.27 into 10 to the power 19 centimeter per centimeter square, or centimeter to the power minus 2, whatever it is. Okay, so 6.27 10 to the power 19. So the value of power is more important than the this constant. So 6.27 10 to the power 19. This is the value of, I mean, number of 12C present per centimeter square of the target file. Okay, so then second, that incidence protons excite the 12C, and de-excitation lead to the production of gamma rays. These gamma rays are detected using a cylindrical cylinder. That means you have this type of cylinder which is made of NaI, and it has the radius of 2 inch. So it has a radius in inch, I think it is given, and length of 4 inch. Okay, and it is placed at a distance of, so if this is the reaction center, it is a distance of 25 centimeter from the target. So this is the target material, reaction center, whatever you can say. Calculate the solid angle subtended by the detector on the foil. Okay, so we have to calculate the solid angle. You know that the solid angle is like this. This is omega. This has been done in the course material itself. I will not go into the details. So if you have the distance d from the center, and if you have the radius r, then or r or a, whatever, then the solid angle can be found. First we will calculate the theta, and the theta can be calculated as tan inverse radius by distance. That means tan inverse a by d, and in our question the a is given as 2 inch. That means 1 inch is equals to 2.54 centimeter. So we converted it into centimeter, divided by 25 centimeter, and if you calculate it, you will get it as 0.20047 radian. Okay, so this was the thing. It was, I mean, if you just consider this particular triangle, so that it is like this. I mean, so this is d, so this is d, this is the thing, and this is a. So from here we have done that tan theta is equals to a by d. That means theta equals to tan inverse a by d. This we have done here. This tells you the theta, the angle only, not the solid angle. So to get the solid angle, we need to integrate over the whole surface. Okay, it is just a 2D picture till now when I am calculating the theta, but solid angle is a picture in 3D. So from 2D we have to do another integration which will convert us into 3D, and that integration has already shown. I cannot, I have just forgotten right now. So ds by r square like thing there was, I will not write if you go to the course material, but the result comes out as 2 pi 1 minus cos theta. If you know the theta, this will be the value of the solid angle which can be calculated by that integration. It is done in the course material itself, so that's why I have not done it here. So 2 pi 1 minus cos theta, that means 1 minus cos, and remember it is in radian, right? Cos 0.20047 0.47 in radian of itself. So just if you do it, you will get 0.1258 steradian. This is the answer for the solid angle. So first we calculate the theta, then using the theta and using the 2 pi 1 minus cos theta, which is a standard formula for the solid angle of this type of system, which I have shown in the figure, you can calculate the value of solid angle. Okay, 0.1258. This one. So this is the answer. Okay. Now third one, it has been asked that beam current of 10 nanoampere, that means I is given as 10 nanoampere, that means 10 into 10 to the power minus 9 ampere. Okay. Is incident on a target foil for 60 minutes. So T is 60 minutes, that means 3600 seconds. Calculate the charge collected by the charge. Oh, we have to just calculate the charge. So charge is actually Q is equals to I into T, where I is the current, T is the time of collection. So your current is 10 to the power minus 9, 10 into 10 to the power minus 9 ampere. Time is, this is very easy problem, 3600 second, which will give you the ampere second is actually coulomb. It is a unit of charge. So 10 to the power minus 5 coulomb. If you calculate 3.6 10 to the power minus 5 coulomb. Okay. So this is the answer for the third one. Okay, now let us go to the fourth one. Okay, so absolute full energy peak of the detector is at 4.43 MeV. Just a second. Yes. Absolute full energy peak efficiency of the detector 4.43, 9.64, 12.7 MeVR. So three values of peak efficiency is given: 0.9%, 0.5, and 0.01% respectively. I think they have not mentioned. Yeah, respectively will be there. The gamma ray spectrum acquired for 60 minutes. So time is also given. Consists of three major gamma rays: 4.43 MeV, 9. So those values which are given there. So three different peak efficiency has been given with three major gamma rays. Okay, and we have to calculate for a single. So there is no need of giving 9.64 and 12.7 for this particular problem, because it has been asked for the cross section for only 4.43 MeV gamma ray. So if you want, you can do it for others also. Just the values are already given. So you know that d sigma by d omega is yield not yield by np nt sigma epsilon, where the epsilon is actually the efficiency, which is given as 0.9%, 0.5, and 0.01. Okay, and sigma is the solid angle, np and nt the number density of projectile and target, and yield is the yield. You know what is yield, and yield is also given that 4.40, the yield is 1.2 into 10 to the power 5. So number of counts is actually the yield. So np nt sigma epsilon, this will be the our result. Now np, that we will calculate by q by c, that is the total collection of charge divided by the individual charge, which will give you the number. Okay, so the number q is given as, and one thing I find it really very wonderful thing, that this is the continuous problem. So here there is no q value is given. Actually these 2 and 3, these two problems are associated with the fourth problem. So this is a continuous problem, different part of a problem. So for q we will use this value 3.6 into 10 to the power 5, but this should have been mentioned it clearly that it is a continuous problem. And you know the charge of particular electron is 1.6 10 to the power minus 9, which will give you 2.25 into 10 to the power 40. Okay, yeah, that is np. nt is also, oh, so this first one, I mean 1 2 3 are continuation problem of which is required for the 4. So nt, the number of 12 nucleus in the target foil, we have also calculated at 6.27 10 to the power 19 centimeter square. So you can see we are taking those values which we have done in the first three problems. It is a continuous problem. Okay, that Mylar compound which has been used in first question. Okay, and the efficiency for 4.43 MeV, it is given as 0.9%. 0.9% means sorry, 0.009, sorry, 009, I think, yeah, 0.9%. Okay, and the solid angle which we have calculated in the third problem or second problem, that is 0.1258 steradian. So we will use all these values which we have calculated earlier, and that will give us d sigma d omega is 1.6 10 to the power 5 divided by 2.25 10 to the power 14 np nt 6.27 10 to the power 19. Okay, and solid angle is 0.1258 and epsilon is 0.009. Okay, so this is the thing. Just a second. Steradian. Yes. Oh, this is not centimeter square. This is 1 by centimeter square. So the unit will be it has a 1 by centimeter square unit. So that means it will go up and it will become centimeter square, and this steradian, it will be in the denominator. So the unit will be centimeter square per steradian, and it is consistent with this particular thing also, because the numerator d sigma is actually the cross section, whose unit is centimeter square, and omega is the solid angle which has a unit of steradian. So centimeter square by steradian is a correct unit, and if you calculate it, you will get 7.5 10 to the power minus 27 centimeter square steradian inverse. That means you can write it like this also, 10 to the power minus 24 centimeter square steradian inverse. So 10 to the power minus 24 centimeter square can be written as millibar. Sorry, bar. So it is also a unit of area which is like this, 10 to the power minus 4 centimeter square. Okay, so 7.5 into 10 to the power minus 3 bar per steradian inverse, and 10 to the power minus 3 bar is also a millibar. So at last you can write it 7.5 millibar steradian inverse. Okay. So 7.5 millibar steradian inverse. It is the unit of d sigma by d omega. Okay. Okay. Now coming to the fifth problem, calculate the total cross section. So here we have calculated the d sigma by d omega. Now we have to calculate the total cross section. So how we will calculate the total cross section? We will just do it, we will just integrate the values d sigma d omega over the total angle. That will give us the value of sigma. That is sigma total. Okay, and it will be, and the integration will be 0 to 4 pi, as you know that solid angle goes from 0 to 4 pi. So sigma total will be 0 to 4 pi d sigma d omega, which we have been calculated, 7.5 millibar steradian inverse times d sigma. So 7.5 millibar steradian inverse will be outside, and d sigma 0 to 4 pi, this value will give you 4 pi. 4 pi steradian, not only 4 pi, times 4 pi steradian. So this steradian inverse will be cancelled out, and the value will be 4 pi into 7.5 millibar. Okay, that is 94.24 millibar. So you can see we have converted from millibar per steradian to millibar only. The steradian part is gone due to the integration over the whole solid angle. So 94.24 millibar is the answer. So these are the main numerical assignment problems. Now there are some theoretical questions also. I will just only tell you the answers of this particular problem so that you can compare with your answer sheet. That is, if the number of nuclei in target foil is more, then more reaction will occur. This will lead to, the answer will be no change in the cross section, because the cross section will not change. It does not depend on the number of the target foil. 7 is, which of the following is a drawback specially for the activity method? So the drawback is the product of the reaction should be radioactive, because their activity is always associated with the radioactivity, radioactive materials. So it is also a drawback. Just go through those theoretical backgrounds which has been covered, which has been taught in the week 8 material. You will understand those answers. I will not go deep into these things. So number 8, that is, in the time of flight method, the start signal is generated by the gamma detector. Okay. The 9th one is, for the radioactive ion beam to be useful, the answer will be this, B. So I have just marked the answers for this particular questions, that the half-life of the radioactive ion should be significantly large than the transit time through the accelerating and transmitting section of the accelerators. And the last question is that in the time of flight method, the stop signal, so it was for the start signal, the 8th one, and the 10th one is the start signal. So the detector far from the neutron source, that will create the stop signal. So these are the answers of the last 5 theoretical questions. Okay. Now just one more thing. Yeah, so this is another problem which is related to the detector, and it is more or less related to this type of problem, d sigma d omega calculation, but I have not covered in the last class, so I will do it. That it has been said that a gaseous tritium target is bombarded with monoenergetic deuteron, that means 1H2, this is the bombarding element, and 1H3, this is the target element. This reaction is happening, this reaction is given itself, okay. So the tritium nucleus, and it is the product, and in the collision alpha particles and neutrons are produced. Okay, fine. What is the neutron rate in a detector at 30 degrees? So this is the problem. This is the bombarding element, this is the target, the reaction is happening, and the detector has somewhere like this, which is at an angle of 30 degrees. So this is the situation. Okay, and having cross section, so cross section of the detectors is given, that means the area 20 centimeter square, and thickness and the distance from the target, so all those are given. Okay, so and the target thickness is also given. Differential cross section for 30 degree angle, because d sigma d omega is a function of angle position, so that's why it is given for 30 degree angle. It is 13 millibar per steradian, and beam intensity is 2 microampere. So we will calculate what is the neutron rate, that means neutron per second, which has been captured by the detector at 30 degree. Okay, so the neutron rate per solid angle can be expressed like this, neutron rate by solid angle. So d and dt is giving you the rate, that is number per second, and d omega gives you the number per solid angle also. So the whole the expression has a unit of number per time per solid angle, that is the neutron rate per solid angle, and it can be written as d sigma by d omega dnb by dt into ntl. So this can be expressed like I have written here. So number of neutrons, that can be written in terms of number density of bombarding element and the target element, which is expressed by the small nb and small nt respectively, along with the distance of the detector. So this is the expression. Okay, and I will write that small nt is number of target nuclei. For our case, it is 1H3 per volume, and number of target, yes, and just a second, if there is any mistake by NP, just let me do it in NP and yes. So yeah, it is correct. So NT can be expressed as NA by A times rho, where A is the area of the target element. Okay, so this we will use, and dNB by dt, it can be written as I by E, which is the deuteron beam intensity, which is the projectile beam intensity actually, and the solid angle I will not do this problem because it is not relevant to this course. Okay, so dNB dt deuteron beam intensity, and the solid angle is delta omega, which can be written as S by R square, where S is the distance from the target material and R is the radius of this particular thing. Okay, so this is the expression, and from here we can calculate dN dt as d sigma d omega times S by R square. So you can see that here I have written dN dt, I mean dN by dt d omega, but here I am writing dN dt because I have taken the d omega on the other hand of the equals to sign, and I have written it by S by R square. Okay, and all the other things are there, Na by A into rho L. Okay, so and the values of I is given, E you know, which is the charge of an electron, A which is the, I mean just a second, A is by R square, yes, R is also given, which is 3 meter, so 3 meter, and Na is the Avogadro number that is known to you, and rho is also given, rho L is also given 0.2 mg by centimeter square. So all the values are given, we will just put it. S is 20 centimeter square, it is also here, so just put it and you will get the required answer. Okay, so d sigma d omega is also given 13 mb by millibar by steradian. So 13 millibar by steradian means 13 into 10 to the power minus 3 into 10 to the power 24 centimeter square by steradian times S is given as 20, you see S is 20 here, R is 3 meter, that means 300 centimeter square. So we are taking the CGS unit. Okay, so length will be in centimeter, and yeah, that is all, and current will be in ampere. So S by R square is there, current is 1.6 2 microampere, that means 2 into 10 to the power minus 6 ampere. Okay, and E is 1.6 into 10 to the power minus 19 coulomb, energy of an electron, and so Na, that is 6.023 into 10 to the power 23 divided by A is given as 3, and rho L is 0.2 into 10 to the power minus 3. I mean A is 3 in the sense A is the value of the target material's number, and this is 3. So that's why I have taken that A is 3, and 0.2 into 10 to the power minus 3 is the value of rho L, which is also given 0.2 in milligram. I am converting it in CGS as I told you. So in 10 to the power minus 3 gram per centimeter square. Okay, so all this I have given. So here I forgot to mention that A is actually the mass number of the target nuclei, which was 3 for our problem. So all these values, if you put it, you will get the value of 1.4 times 10 to the power minus 3 per second. So this is the number of product which is Newton, that is captured by the detector, which is placed at an angle of 30 degree from the center of the I mean reaction. So this type of problem you may also face. So this problem have also been taken from that particular book which I showed you, and you can find it in the drive which will be shared by you also if you want, but and it is a popular book, you can download by yourself also. So these were the all materials which I wanted to cover. So I have done some of the extra problems associated with the kinematics of the nuclear reactions. I have gone through the theoretical and background of the kinematics also, different conditions, and based on that threshold energy value problem, some different problems also, example 1 2, then this radiation matter interaction or light matter interaction, what you can say, this type of problem, radiation detectors, time of flight type problems, and also the assignment problems. So by doing this I will end today's class, and as it was your last tutorial, so we will not meet again from the next week, but I wish you all the best to everyone for your upcoming exam. And if you have any questions also before your exam, you can mail me to my mail ID. Just again writing sourabhadra@iisc.ac.in. So in this mail address you can ask anything if you want before your exam. So all the best for your exams, and I will thank you for attending tutorials. Okay, bye, goodbye. I will end the class here.